Hello and welcome. In this video, we will explore an important property of vector fields called the divergence. The divergence of a vector field is a scalar quantity measuring the extent to which a particular point in the field behaves like a source or a sink. For example, in this vector field, the specified point behaves like a source. That is, the arrows seem to be flowing away from the point. More precisely, if we put a small boundary around the point, the arrows push outward through it. When this occurs, we say that the divergence of the field at the point is positive. In this vector field, the point behaves like a sink, with the arrows flowing toward the point. Again, if we put a small boundary around the point, then the arrows push inward through it. In this case, the divergence of the field at the point is negative. In this vector field, the point seems to behave like neither a source nor a sink because the net flow into the boundary appears to be the same as the net flow out of the boundary. Here, the divergence of the field at the specified point is 0. At such points, the field is said to be divergence-free. For reasons we'll see later, in fluid mechanics, a divergence-free field is often called incompressible. And in electricity and magnetism, divergence-free fields are sometimes called solenoidal. Please note that all these ideas also apply to three-dimensional vector fields, but it's just easier to visualize with two-dimensional fields. As a further example, let's look at this vector field. In particular, at this point. Try to decide whether the divergence of the field at this point is positive, negative, or 0. Imagine putting a small boundary around the point, and think about how the arrows cross the boundary. Pause the video to think about it. This point very clearly behaves like a sink, and the divergence at this point is negative because the arrows flow into the region around the point. Now try to decide the sign of the divergence at this point. Pause the video to think about it. It's not quite as obvious in this case because some of the arrows flow out of the region while others flow into the region. However, the arrows flowing into the region have a larger magnitude than those flowing out of it. So on average, there is more inward flow. This means that the divergence is negative at this point. Now what about the divergence at this point? Please pause the video to think about it. This point very clearly behaves like a source, with the arrows flowing out of the region. Therefore, the divergence at this point is positive. At this point, the divergence is also positive. Even though some arrows flow into the region and others flow out, the outward arrows generally have a larger magnitude than those flowing in. So on average, this point behaves like a source. This one is interesting. What is the divergence at this point in the field? Pause the video. The divergence at this point is 0. Some arrows flow in and others flow out, but in equal amounts. The divergence at this point in the field is also 0 for the same reason. Sometimes it can be hard to tell visually whether the divergence is positive, negative, or 0. For instance, at this point. The flow through the left boundary seems to be a little stronger than the flow through the right boundary, and the flow through the bottom boundary seems to be a little stronger than the flow through the top boundary. But whether the inward and outward flows cancel on average is not nearly as clear as in the other cases. At this point, the divergence is indeed 0, but moving the point just a little bit up produces a negative divergence, which is not at all clear graphically. Moreover, there is actually more to consider than just the magnitudes of the arrows. The angle at which the field slices through the boundary is also a factor. Flow that crosses the boundary at or close to a right angle has a greater effect on the divergence than flow crossing the boundary at a shallower angle. This subtlety will be made clear in a future discussion about a concept called flux. Also, the divergence is a local property of a vector field, meaning that it is completely determined by the behavior of the field very close to the given point. So, it will be important to take a limit as the boundary contracts around the point. This is not an issue mathematically, but the resolution of the plot somewhat impairs our ability to analyze this visually. Since it can be difficult to analyze the divergence graphically, it is important to be able to calculate it. For a vector field with components f1, f2, and f3, we can compute its divergence by taking the partial derivative of the first component with respect to x, the second component with respect to y, and the third component with respect to z, then adding these derivatives together. Fortunately, this is usually a very straightforward computation. There is another common notation for the divergence involving the del operator, which uses vector notation and places the partial derivative operator with respect to x in the first component, with respect to y in the second component, and with respect to z in the third component. This is not really a vector, but we can pretend like it is and compute the dot product del dot f, interpreting multiplication as the act of computing the derivative. That is, del dot f evaluates to df1 by dx plus df2 by dy plus df3 by dz, which is just the formula for the divergence. If we want to emphasize that the divergence is being computed at a specific point, then we can do so using function notation. Physically, the divergence can be characterized as the negative rate of change of the density, or concentration, of mass in a small surface of constant volume around a specific point. If the divergence of the field is positive, then the field is, on average, pushing mass out of the surface, decreasing the density of the contained mass. Conversely, if the divergence of the field is negative, then the field is on average pushing mass into the surface, which increases the mass density. This behavior is quantified by the so-called continuity equation, which appears often in physics. This equation also explains why a divergence-free field modeling a fluid is sometimes called incompressible. The continuity equation says that incompressible fields have constant mass density throughout transport, meaning that a given mass of fluid does not compress into a smaller volume, nor does it expand into a larger volume. Soon we will make these ideas more rigorous via the third big integral theorem of vector calculus, aptly named the Divergence Theorem. So stay tuned, and thanks for watching.